Hello, DataCamp AI. I am Camp Fauss. I am a fourth-year PhD student at the University of California, Santa Barbara, and I have spent the last 4 years studying and applying machine learning techniques to look at the field of critical conditions around wildfire in Southern California. And I hope to bring to this position my 4+ years of experience in computational studies, as well as more than 2 years of teaching experience, including in-person and remote. And I am looking to gain professional experience in the field of data science. Most of my experience thus far has been in academia, which is great for learning, but I'm really curious to see what's out there in the professional field and get a taste of industry. So next we have K-means clustering. So again, I'm going to look at this topic and try to break this down in a way that a 13-year-old or your grandma can understand. So the kind of how I usually start this out is with something engaging to get the students kind of looking at the material and thinking about it. So first, I have this idea of clustering. And what is clustering? We have this figure on the right that shows you guys kind of two different types of dots. And your first thought here is to look at these dots and think about how many groups would you sort them into. And I may have given that away there, but I invite you to take a minute to think and put in the chat or say out loud how you guys might go about grouping these dots. And then this is how most people would do it. So you have K means K equals 2 for this group. And you can see that this group sorts very nicely into two groups by size. But it is not always that simple. And here you can actually see we have dots of varying sizes. So we're going to take another minute here for you guys to think about how you would go about grouping this set of dots. And I'll give you a minute to think. And feel free to post your ideas in the chat as we go. And now you can see this is not so clear. These are the same dots, but now I've kind of organized them on a gradient of size, but it's not immediately obvious how many groups like pop out here. So this gets us thinking about the idea of K-means clustering and how this can be useful. So you could see maybe there are 2 groups, maybe there are 3 groups, and ultimately we're going to try to use math to help us find the absolute best number of groups. And this is what this looks like. So now we have groups plotted along the X and Y. We have 2 different dimensions to our data, and this may be known, it may be unknown. You could think of it as like size and length or weight and height, but it could be anything. And now we're going to think again about how many clusters can we organize this set of dots into. And you can see again, it's not incredibly obvious. There could be 2, there could be 3, and I've used colors here to kind of indicate these. So now we get into this true idea of K-means clustering. So there are a couple steps to this, and the first one is going to be thinking about how many groups you might use. For this, we've chosen to move forward with 3, and then you're going to try to plot your centroids. So you're going to try to guess where the middle of these groups might be. And our initial guess here, marked by these stars, does not look very good, but that's okay for now, and you'll see why in a minute. So the next step is to use distance to assign these points to their groups. So you can see here this complicated distance formula, which I left up there if you're curious about it. But essentially, we're going to calculate the distance between this point and each star that we guessed earlier, and then assign that point to the star it is closest to. And we're going to go through each of these points and repeat that process until we have labeled each point with its group. And you can initially see like we did an okay job, but I think we can do a lot better. And that's kind of where we get into the next idea, where we're going to start moving our initial guess of these centroids. Now we use this formula to calculate the location of that centroid. And again, you don't have to kind of know this formula right away, but I want you to get an intuition for it. So we guessed where these centers would be, and now we're actually, after we've assigned all these points, we are going to recalculate the center of each of these clusters. So we do that, don't kind of get hung up on that, but notice that after we've kind of calculated the objectively correct centroid, that some of these points are now closer to different centers. And the next step in our process is to come through and take those points and reassign them to the group that they now belong to, again by distance. So notice that these 2 points used to be closest to the orange star, and now they're closest to the green star. So now we are going to reassign those points as green, or I'm sorry, they used to be closest to, yes, the orange star, and now they're closest to the green star. So we reassign those points as green, and we move to the next stage of our analysis. So now we want to iterate that process. So we're going to keep taking those points and we assign them to the center that they're closest to. And then we check, do we need to recalculate our centroid? And we're going to repeat that a couple times where we recalculate that centroid, and you can see the stars move again, and then check again to see, do we need to add another point? And you can see one more orange point flipped from the orange group to the green group. So we repeat this process, we move those centers again, we recalculate where they belong, and we keep doing this until we reach something called convergence. So this is the point at which our centers are stable. These points, we never end up with like a better situation here on this run where we want to move another point from one group to another, or we want to move another centroid. So we have converged, our situation is stable, and this was kind of the best thing that we found for this group. So what I would ask you now is, how do you feel about these clusters? And then how do you think we could quantify how good we, assign these clusters? Like, if you look at this, you can kind of get a gut sense that something's still not quite right here. And that's something we're going to explore a little bit further. So I'll give you guys a minute to think about that. You can post things in the chat if you have questions or ideas. And then we move on to looking at something called the within cluster sum of squares. So there are so many different ways that we can look at the goodness of our clustering. And again, we're not going to get too deep into the math here, but just know that there are a bunch of different numbers that we can calculate here that tell us like how good a job we did at clustering. Do we think this is really reasonable for the purple cluster versus the orange cluster versus the green cluster? And there's a really cool way to visualize this. So now we're going to look at a visual representation of how good we did with our clustering. So this is built off this idea of minimizing the overall variability. So we want to kind of define our clusters to have the smallest spread within that cluster. That's kind of the metric we picked to move forward. So for this, you can actually see, comparing these two new sets, our first grouping for this set, we probably have too many points in the orange cluster, and we probably don't have enough points in this purple cluster. So each color bar underneath these points represents that like spread or variability. And this bottom here shows you kind of all of those things lined up. So this little frowny face shows that like we did not do so great with that initial guess. That's a really large spread. But simply by reorganizing these groups, we get a much smaller overall variability. So we've done much, much better in the second one. So we can now take this idea and apply it to our two-dimensional data. And you can see now that we have this worst guess. So this is kind of our first guess, a better guess, and our best guess. And what this is actually doing is we're kind of looking at the final play out of our clustering, and notice that our initial one was actually pretty bad. And then if we do something a little different, we can get one better. And then our last one is very close to like the optimal grouping. But how did we do this? The way we kind of think about this, if you guys remember how this all started, was we picked these initial guesses. You took these stars and you put them on the map. And that can actually be done differently. And the way your computer actually does this is it places those stars randomly. And depending on where it starts with those stars, you end up with better groupings or worse groupings at the end. So what happens here is your computer's going to make a whole ton of guesses and get a whole ton of like outputs of final groupings. And eventually you're going to find one that has the lowest final variability in these groups. And that's what we'll define as our best. So there is one more step here, and that might be, you guys might be able to see it coming. We can choose different numbers of groups. And the way we do this is we're actually going to calculate our best overall clustering for different numbers of groups, and then take that metric, that variability metric that we calculated earlier, and plot it for each one of those groups. And this is really where you get to the power of k-means clustering. And you can see here that given our groupings, and given kind of how our plot played out. And this is called an elbow plot because you typically don't want to choose a point that's very high, and you'll notice that this thing kind of converges to zero. The more and more groups you add, the less and less variability you have in those groups, but also the less meaningful those groups are. You can define a k-means cluster with a cluster for every single point, but that's not going to tell you much about the data. Typically, we want to choose the number of clusters at the elbow in this elbow plot. And that's what this looks like. So for our data, it looks like K groups of 3 was actually the correct, or at least overall best grouping that we can come up with.